Hi and welcome to my fourth video about the best methods to acylate amines. This presentation is about the direct conversion of carboxylic acids into amides without the use of stoichiometric amounts of a coupling or activating reagent. These reactions often require harsh conditions unsuitable for the preparation of peptides or beta-lactams. For less sensitive amides, though, the direct acylation of amines with acids can be an inexpensive alternative to the coupling strategies discussed in the other videos of this playlist. Carboxylate anions are weak electrophiles and can only be condensed with amines at high temperature, usually above 160 degrees Celsius. There are, however, some Lewis acids capable of activating carboxylates even in the presence of amines. The carboxylate Lewis acid complexes are more electrophilic than simple carboxylates and enable amide formation to proceed at lower temperatures. I'll show you some examples in a minute. The main advantages of this strategy are that no water-sensitive reagents are required and that the only byproduct is water. No expensive or toxic coupling reagents are necessary, making this an affordable and simple approach to the preparation of amides. Disadvantages are mainly the high reaction temperature and long reaction times. For some of the newer catalysts, the functional group compatibility is not known, and many of the newest examples require large amounts of molecular sieve. Weak acids form acylium cations more readily than stronger acids, and will usually undergo thermal condensations faster. Nevertheless, most carboxylic acids can be converted into amides by heating with an amine to about 180 degrees Celsius, as in this example. If acids are heated with amines in the presence of alcohols, amide formation may also proceed by intermediate formation of esters, which are better electrophiles than carboxylate anions. In this example, amide formation required heating to 160 degrees Celsius for 6 hours in an autoclave. If the acid is weak and inexpensive and easy to remove from the product, then thermal condensations may also be conducted in the presence of a large excess of acid, as in this example. Silica gel seems to have a moderate catalytic effect on the thermal condensation of carboxylic acids with amines. Still, refluxing in xylene for 2 days was required to attain a yield of 77%. These thermal condensations are nothing new and have been used in the chemical industry for many years. Plenty of potential catalysts were tested, and in this patent of the 70s, zirconium and titanium alkoxides were reported to promote thermal amide formations. Interestingly, the inventors found boric acid and aluminum oxide to be less effective, although later boric acid was repeatedly used by others as catalyst for amide formations. This is a more recent example of the use of a titanium alkoxide as catalyst. Here, the reaction already proceeded at 70 degrees Celsius, but a large amount of molecular sieve was required to attain high conversions. With a hafnium-based catalyst, acids can even be condensed with amines at room temperature, but again, only with a large amount of molecular sieve. Because of the lower temperature, Bock-protected alanine could be used as a starting acid. Another class of catalysts that promote amide formation already at room temperature are 2-halophenyl boronic acids. Unfortunately, again molecular sieves and a large amount of catalyst were required, but the molecular sieve may at least be recovered and regenerated. Aryl boronic acids, however, are not stable and slowly undergo carbon-boron bond cleavage in the presence of water or other protic solvents. An excess of strong mineral acids does usually not bring about the condensation of aliphatic amines with carboxylic acids. The concentration of a free amine under such strongly acidic conditions is usually too low. Thus, when a mixture of benzoic acid and aniline was heated in an excess of polyphosphoric acid, no benzanilide was formed. With less basic amines, however, a larger fraction of amine will remain unprotonated and available as nucleophile. Treatment of 4-nitroaniline with benzoic acid in polyphosphoric acid, for instance, gave a substantial yield of anilide. Anilines of very low basicity, such as 2,4-dinitroaniline, almost behave as alcohols or phenols and undergo quantitative acylation by acylium cations generated by strong mineral acids. Thus, if the acylation of some non-basic aniline or diaryl amine does not proceed well under neutral or basic conditions, the use of strong acids as catalyst should be considered. So, what can go wrong? During purely thermal or acid-catalyzed condensations, a large number of other reactions can occur, such as eliminations or dehydration, rearrangements, isomerization, for instance of double bonds, or fragmentations. But with the newer catalysts that work below 100 degrees Celsius, these side reactions may be less of an issue, and the scope of acceptable functional groups should be larger. Not only the starting materials, but also the products may undergo cyclocondensation or other dehydration reactions. One specific example would be the formation of imidazolines from carboxylic acids and 1,2-diamines, as shown here. In this example, boric acid was used as catalyst in refluxing xylene. Here's a short selection of some further, mostly recent examples, which you can also find in the description of this video. The next and last presentation of this playlist is about acylations with the aid of carbon monoxide and oxidative acylations with aldehydes. For smaller laboratory preparations, these strategies do not usually offer any advantage if compared to the use of conventional acylating reagents. But for large-scale preparations, carbon monoxide can offer an inexpensive alternative. See you then.